Hey there, chemists. In our last lesson, we looked at radical halogenation reactions and how we can replace CH bonds with C halogen bonds, things like chlorine and bromine. Today, we're going to look at what's the difference between some of these halogens and how do we predict what our major product is if there are multiple constitutional isomers. The first thing to pay attention to is that not all radicals are created equally. The more substituted your radical is, the more stable it is. For example, on the left here I have a tertiary radical. That's a carbon with a dot and 3 carbons attached to it. That's why we call it tertiary. That is more stable than a secondary radical with only 2 carbons attached, which in turn is more stable than a primary radical with only 1 carbon attached, which in turn is more stable than a methyl radical. That's the least stable of the options in front of you. We can actually see the stability if we look at the energy associated with the bonds. If you try to break a bond, here are 3 different CH bonds, primary, secondary, and tertiary, and they don't all have the same energy. It's easiest to break the bond that forms the most stable radical. Let's write that down. So tertiary CH bond is easiest to break because the radical is stable. Frankly, more stable than a secondary or a primary. So we're going to use bond association energies to quantitatively look at the differences that we see in the propagation steps for these radical reactions and ultimately try to explain why we see differences in product distributions. So let's take a look at what happens when we do a radical reaction on a molecule or more than one product is formed. So here's the chlorination of propane. Now, propane has a total of 8 hydrogens, but if I just draw in what they are, they're not the same. There's 3 primary H's on the left, there's 2 secondary H's in the middle, and then there's 3 primary H's on the right. So we've got 6 primaries and then 2 secondaries. So I might expect to see a 6:2 ratio of the primary product, the 1 chloro product, versus the 2 chloro product. But I don't see that. It's not a statistical breakdown based on just the abundance. And what's more is we actually see a majority of the more substituted product. I get mostly the 2 chloro product. Even though there's only 2 secondary CHs, I get much less of the one that seems like it should come from the more abundant H. Well, that does in part have to do with the fact that a secondary radical that's formed along the way is preferred to a primary radical. It also has to do with the bonds broken and formed with these chlorines as opposed to, let's say, bromine. What happens when we switch to bromine? You get a much different, a much more selective reaction where we get primarily the 2 bromo derivative as opposed to the 1 bromo derivative. Nowhere near the statistical abundance of 6:2. It's 3:97. So what we're going to do is look at some delta H values for the steps that lead to these products and ultimately try to realize something about types of reactions and their selectivity when they make different constitutional isomers. That's what these are, right? These are constitutional isomers. Okay, so let's start by writing out the propagation steps of how we form these products. Remember, the propagation is not the initiation and not the termination, it's just the middle part of the mechanism. It's where you've already generated a halogen radical and then it sees an alkane. So to make the 1 chloropropane product, I would start with a chlorine radical that would see the propane molecule. It would abstract an H and become an HCl and turn it into a primary radical. Then that primary radical would see a molecule of chlorine. It'll actually take one of those chlorines, liberating just another Cl dot, and you get your product, your 1 chloropropane product. Remember, these are propagations. Radical becoming a different radical. radical becoming a different radical, and it's catalytic in the chlorine radical. Yes, you could have a termination of the two radicals, and that could lead to the product, but that is far less abundant just in terms of how many equivalents you ever have of a radical at any given time. As soon as it's formed, it's usually used up right away because they're so much less stable and therefore more reactive. So it asks us to calculate the delta H values for this. Now a delta H, a change in enthalpy, is the energy of the bonds that are broken minus the energy of the bonds that are formed, because every time you break a bond, you absorb energy. Every time you form a bond, you release energy. So I'm just going to write broken minus formed. Now, what are these bond energies? Well, they're in that table in the upper right. So we're going to be using this table a lot as we compare the different types of bonds involved in these steps. So in the first step, what bond are we breaking? We're breaking a primary CH bond. What bond are we forming? We're forming an HCl bond. And if I go look at the chart in the upper right, the bond energy of a CH bond that's primary, because that's the one we lose here to make this primary radical, is 98 kcal per mole. And then the energy of the HCl bond that we form, that's 103. And then when I do the math, you get -5. So this is exothermic by 5, and the units are kcal per mole. Now let's look at what the case is for the second half of this propagation. What do you break? You break a Cl-Cl bond, so delta H would be the 58 kcal just from the chart up above. And this time you form this carbon-chlorine bond. That's a primary carbon-chlorine bond, and that's worth 81 kcal per mole. So we release 23 kcal per mole. And yes, we could add those, but I'm going to keep those as is. It's exothermic by 5 and exothermic by 23. That's to form the 1-chloropropane product. What about the other isomer? What about 2-chloropropane? Let's do the same thing. Right below, I have a very similar mechanism. A chlorine radical sees propane. You form HCl, but this time you form a secondary radical. And then another chlorine molecule sees that secondary radical. You form a new chlorine radical, and then 2-chloropropane, the constitutional isomer of the first product. What are our delta H values? Delta H for this first step, well, we broke a secondary CH bond, which is not 98. It's actually a little bit easier to break a secondary. It's 95. Back to what we said in the beginning. Secondary CH bonds are weaker because it's easier to form that radical. You still form an HCl, so I still subtract -103. That means I'm exothermic by 8 kcal per mole for that step. And then for the second step, delta H, you're breaking a chlorine-chlorine, that's 58. You're forming a secondary CCl bond, and that's worth 80, almost exactly the same. 58 minus 80 is -22. And that's our values for the secondary case, -8 and -22. So I just want to hold on to these numbers, and now we're going to compare them with the bromination case. So what I'd like you to do is hit pause and do the same exact thing, except everywhere there was a chlorine, put a bromine, and use the corresponding numbers in the chart up above, and then we'll compare our numbers, and then we're going to graph them and see why switching to bromine makes this so much more selective. Hit pause and get those numbers now. Okay, let's see how you did. So for bromine, we have a bromine radical. It sees a propane. It turns into an HBr and a primary carbon radical. Your delta H values, if you use the numbers, are 98 minus 88, so 10 kcal per mole. The second half of that step would be a bromine, Br2, seeing the primary radical, forming a bromine radical, and then your 1-bromopropane product. Delta H is going to be, you break 46, the Br2 molecule, much weaker energy, and then you form 68, so we're exothermic by 22 kcal per mole. That's to make 1-bromopropane. Now let's do the constitutional isomer. We start with a bromine radical. It sees propane. You make a secondary carbon radical and an HBr molecule, delta H. You break 95, the secondary CH. You form HBr, that's 88. So it's 7 kcal per mole. The second half of this, a Br2 molecule sees the secondary radical. You form a bromine radical and then 2 bromopropane, the other product. Delta H is you break 46, the Br-Br bond. You form the CBr bond, which is still 68, which means you're exothermic 22 kcal per mole. So now we have all these numbers in front of us to form the chlorine products. There's 2 different pathways, the yellow and the blue I've highlighted. And then to form the 2 different bromine products, well, we've got positive 10 and negative 22 for the primary case. And then just to use a different color, we've got positive 7 and minus 22 for the secondary case. I still don't see why bromine is more selective, but there's something very different about the bromination case. Let's visualize this by graphing those energies on some rough energy diagrams. So these are energy diagrams that show essentially energy versus the reaction progress. As you go left to right, you go from reactant to product, and we're going to look at the energy changes as we get from the starting material to the product with the intermediates along the way. So I'm going to roughly sketch just some arbitrary place where the energy of a propane is. I'll just put it there. We'll just say that's where propane is. I'll even put a little propane molecule below. That's what that is. Now, how do we get to the 1-chloro and 2-chloropropane derivatives? Well, look at our numbers up above. To get to the 1-chloro product, we had to be exothermic by 5, and then exothermic again by 23. To get to the 2-chloropropane, it's exothermic by 8, and then exothermic by 22. So let's just roughly sketch that on this graph. So to get to the primary product, we go down 5, so just like a little bit. That's our primary radical. I'll put a little primary radical there. And then to get to our secondary product, it's just a little bit lower. This is just to show relative differences. This doesn't have to be to scale. Then to get to the products, it's even much slower. That's exothermic by 23 and 22 more for each of them. So much lower down is our 1-chloropropane derivative, and then even lower would be our 2-chloropropane derivative. So those are the energetics. That's the thermodynamics, where you start, where your intermediate is, and where your product is. But there's 2 different pathways, and what you should hopefully see is that both of these are exothermic pathways at both parts of the mechanism. And I'm going to very roughly sketch what an energy curve would look like. We can approximate the kinetics with the thermodynamics. You start at some arbitrary place over here, and then you go up some activation energy to get to the first intermediate, and then you go over some second activation energy to get to the first product. That would be the path which the reaction undergoes to get to the primary product in chlorination. What about the secondary product? Well, it's a similar looking path, but it's kind of lower along the way. It's a more favorable intermediate, and thus a more favorable product, it turns out, in the end to get to the secondary case. Let's highlight those just to match our colors up above. Here's the primary product in yellow, and then I forget already we used a light blue for the secondary case, so there's our secondary case. So I'm just going to notice one thing. Both steps are exothermic in chlorination. I'm just making a mental note of that because I see that in the diagram. Now let's draw what we get for bromination right next to it. I'm going to start the same way I did it the first time. We have an arbitrary place where our propane energy is. Now, how do we get to the primary and the secondary bromine products? Well, look at our energy values. Here we have to gain a net of 10 endothermically before we exotherm 22 to get to the primary product. And to get to the secondary product, we have to gain a net of 7 endothermically. in the first part before we exotherm 22 to get the second part. So our graph's going to look a little different. So if I put my energy values in first, our primary product is actually higher in energy up here somewhere. There's our primary intermediate. And then a little bit lower would be our secondary intermediate. This is not perfectly to scale, but just relatively. And then, so it takes energy to get to those two intermediates, regardless if it's primary, secondary. Then it's exothermic to get to the final product. So those are going to be lower in energy. Somewhere down here might be our primary bromination product, and then below it would be our secondary bromination product. And if we sketch rough curves of how we get there kinetically, yes, you're going to undergo some activation energy to get to the primary intermediate, and then some other activation energy to get to the primary product, and likewise a similar curve but shifted down below it for the secondary case, and then ultimately the secondary product. And just to color code them, we have the purple one should match our energies up above for the primary case, and this green one should match our energy values for the secondary case. And the thing that you should notice right away is that here, the first step in bromination is endothermic. And that must be the key. All of that was just to get to this, chemists. All those energy calculations, all that arithmetic, all those diagrams, all these curves and colors are just to say, hey, you know what? When you use bromine, your first step is endothermic. And that is what we use to explain why bromination is so much more selective for the more substituted product compared to the less substituted product. And we can go a little bit further than that and explain why the first step being endothermic is that much more selective. It has to do with these activation energy curves that we drew. And even though we don't have kinetic data, we're using the thermodynamic data to approximate what those kinetic curves look like. When you have an endothermic first step, there is a larger difference in activation energy. In other words, this gap, which discriminates between the two pathways, one of them leading to your primary product, one of them leading to your secondary product. And I'll show that on your notes. Here's a dotted line benchmarking the crest of the primary product, and here's a dotted line showing the crest to get to the secondary product. And it's that gap that I'm talking about. There is a larger difference in activation energy, E sub A, when the first step is endothermic. So as a result, the reaction is more selective for the more substituted product. And you can think about why that is. If that gap is bigger, which we're telling you it is for endothermic cases, why does that make it more selective? Well, you can give the reaction just enough energy to go over the lower energy activation energy, and that makes it easier to discriminate between that and the other pathway, which takes a lot more energy. When your activation energies are closer to each other, which they are for exothermic first steps, it's because you have what's called an early transition state as opposed to a late transition state. When your first step is exothermic and you have a smaller energy difference in the activation energies, it's harder to discriminate between which path it takes. You're giving it just enough energy to go to the lower one. Okay, it's not much more to get to the other one. So as a result, bromination is more selective, and it's simply because the first step is exothermic. First step is endothermic. The first step in bromination is endothermic, right there what it says. Does that mean that we see an even higher selectivity if we switched to a tertiary radical? Absolutely. And then we'll talk later about what happens with some of the other halogens. You know, what does that mean about iodine or fluorine compared to these? We'll get back to that. But that's it for today. Thanks for watching.